name is Kishore Tiwari, and I'm an implementation consultant with the Global Consulting Delivery team here at Autodesk. What you'll learn today is an introduction to Netfabb Simulation. You'll learn why you need Netfabb Simulation when dealing with additive manufacturing, and you'll also see how we can do a quick demo setup and see how to see the results and what you can do as a follow-up after you've done a simulation. So for today's session, with the introduction to Netfabb Simulation, the agenda for the rest of the hour would be as shown on the screen. We'll first understand why we need to simulate, what is the purpose of running a build process simulation when you're dealing with additive manufacturing. We'll then deep dive into a little bit of the modeling theory, what's happening behind the scenes of Netfabb Simulation. And this is important to understand because Netfabb Simulation incorporates a whole bunch of new techniques to get the job done. And the better you know it, the better you're able to use the software to get the job done then. Following which we'll quickly have a look at through some examples that we use to validate these new ways of simulating, jump into the software, see how things are done there, and then move into dealing with the outputs, which are basically compensated geometries. So why simulate? And that's because when you're dealing with additive manufacturing, the four things that you see on the screen right now are the most common ways that your part can fail. These failures are, as you can see, predominantly based on distortion, where your part distorts to a level where it causes a different problem, which could be a Recoater blade interference, where it hits with the moving components of your machine, or it distorts so that it removes away from the support material, or in many cases it just distorts and it's not in spec with what you were actually expecting the output to be. Every now and then you also get failures which are associated with more thermal problems, which is identified as hotspots and lack of fusion. And these basically don't distort your part so much, but they still compromise the quality of your part and are undesirable. And what can these failures cost? These are just some rough numbers in front of you, where a small part like this, printing it once can cost around $6,000. I'm talking about the example at the bottom. And then you print the part, you manufacture it, you see what the problem is, you then make the right corrections, and then you print again. And then the total cost becomes around $12,000. However, if you simply run a 15-minute simulation, you could have saved half the cost. You could have got the job done in the first time without having this first unsuccessful event. And that's the purpose of simulating. It is to save as much time and money that you can and get your additive build right the first time. How should you go about simulating and build for the DMLS process? Now, ideally, you would want to map this entire workflow as is shown on the screen right now. And that means you understand the parameters with which your machine is printing your part. You understand the material properties that you're trying to print, combine those two, and then you come up with the heat transfer or the temperature history model of your component. Based on that, you then calculate the mechanical response. And then based on that, you keep adding that on top of each other till you get the final output. Now this, as you see, is a very tedious process because this involves doing this process layer upon layer. This building up of the temperature history, if we take this to be a part, has to be done across every layer. So this is layer 1, then layer 2, then layer 3, and this keeps going on and on. And the mechanical response that we need to calculate based on this temperature history is essentially how much is your part or how much is that layer expanding and contracting. And you need to keep in mind that based on the previous history of the layers that you have built up, each layer is going to expand and contract differently. And that is what leads up to this deformation. And that is how you would model this complete process. Now, what is the problem with trying to model this complete process? it is extremely computationally heavy. Let's take this really simple 4-inch by 4-inch block for example. You will end up modeling around 9 billion nodes, and I think that is 200 trillion terabytes of data. I might get my zeros wrong, but you can count them over there. And as it shows over there, that is approximately 10% of the whole of internet from 1 decade ago. It basically means that to solve something as simple as a 4-inch by 4-inch test piece, doing this solved layer by layer, doing it with the workflow and the process described in the previous slide to get the most accurate results, you have to solve way too much data. And that just is not feasible if you're trying to actually simulate proper parts, not just simple 4-inch by 4-inch parts for your additive manufacturing build. And therein lies the need for an innovation, and that's what we did with Netfabb Simulation. So one thing that Netfabb Simulation does differently from all other general purpose solvers, in my previous example, what you saw was the solve times and the data needed to be solved on a general purpose solver. Hence, I'd used the terms like ANSYS or Abacus. But what we do in Netfabb Simulation differently is we use a very specifically engineered element called the hexate element, which has one thing that it does really well, and that is called adaptivity. What is this adaptivity? Adaptivity means you get to have large elements in the areas of the build that you've already finished solving, which are areas like this, or areas of the build that don't really matter, which are the build plate, for example, while maintaining really small elements and a fine resolution for the areas of interest, which in this case is the layer that is being solved right now. So as you can see that in the area which we are solving, which I'm shading right now, you can see that the number of elements is very high and their resolution is very fine. But in the areas where we have already completed solving, the elements have drastically increased in size and they're much larger. This means that we don't really need to maintain a high number of nodes or a lot of data to solve throughout the process of simulation. We can choose to basically hone in, really be specific about where we want lots of information from. But once that information has been derived or calculated, we can choose to break out the elements into something larger and then go on to the next solve. What does this adaptivity look like? It means when you're solving a particular layer, that's where most of the fine elements are. But once you're done solving, it goes away, as you see in the left-hand side image. And then as you keep building on top of that, you will see that only the layer which is being solved has the fine elements. Everything below that just automatically keeps getting larger and larger. And that means you just have less data being stored, less data being solved at any given point of time of the simulation. Now, how did we test this out? How did we validate that this new element that we have made, is it doing the job or not? We tested it out on a DED process simulation. Now, why did we choose DED process? That's because it is very similar to the powder bed additive process, which is what the 4-inch by 4-inch example was that we previously saw. However, the DED process, the heat source is significantly larger and moves much slower. And that means that a solve is basically simpler to do, and hence it was a good candidate to use this new element on. And as you can see, that we managed to complete a solve of a pretty large part, which was around 4.5 meters long, a couple of meters wide, and tens of centimeters thick within 1 day on a regular workstation, which is a regular 16-core machine. And we didn't just complete the solve, but as you can see, we also managed to get the solve to predict very closely what was happening in real life. The solid line that you see is the physical experiment that was conducted by printing the same part. And the dotted lines that you see was the prediction of the solver using this new hexate element with high adaptivity. And you can see that it is very closely following the trend, and in many points, it's also very much the same as what was actually happening in real life. So now that we managed to solve this problem of having less data, or kind of processing less data, we tried to apply it back into the 4-inch by 4-inch test cube for a powder bed additive process. And as you can see, while we have significantly reduced the amount of data to be solved, it still is pretty high. It's not something that you can simply pass to a regular laptop, like the one that I'm using right now to do this, or a workstation. It does require some specific hardware to be set up to solve these kind of problems. And that's not something that's acceptable, because additive manufacturing is so commonly used right now that it should be solvable in pretty much every kind of laptop or workstation. And it's for that we came up with this second bit of innovation, or it's not so much of an innovation, we simply adopted a way of solving the problem, which is called multi-scale modeling. Now, what is this multi-scale modeling? It simply means that we do the hard or the difficult part of the solve only once and at a much smaller scale. That is what you're seeing right now. You're seeing that we have captured the process parameters. If you remember, this is something that I had highlighted at the beginning, that we need to understand how does your machine make the tool path, and understand the exact model of the material that you're trying to print. That is what we are doing right now in this small scale, or this tool path simulation that you see. We are basically at a very, very small scale solving what happens when you print the material with the process parameters like the power, like the scan speed, like the laser thickness that your AM machine has. Once that is solved, we save it into what we call as a PRM file, so that we can then apply it to larger scale simulations how many ever times we want. That means we solve the PRM file once and save that, but every time we solve a much larger file, as you're seeing on the right hand side video, that is simply copying values from this PRM file and applying it at a much larger scale. And this process happens a lot faster because you don't need to calculate the tool path while you're doing this large solve. As you can see, with the large part, we managed to solve a part which is around 125 mm wide and the same dimension in length, and I think maybe 80 mm tall, in around 4 hours on a 14-core workstation. Now, what or how this information is transformed between the PRM file and the large scale, the way that I explained it right now, it was a lot of paraphrasing and very loosely defined terms. And that's because exactly how this process works is part of our IP. But as I'll show you in the next few slides, that this novel way of doing multi-scale simulation, where we do the difficult part of the solve at the small scale only once, and apply those learnings on a larger scale how many ever times you want to, has been validated, and it does work. And it works with really good speeds. As we were seeing over there, or in the previous examples and slides, of how even a 4-inch by 4-inch part produced so much data that it was impossible to solve of sorts. We see over here a more complicated part, which has lots of lattices on the inside, which is significantly big, as you can see the dimensions on the screen, which completed a run on a 20-core machine in 11 hours. It's going to take significantly longer to build it, but in, I would say, a third of the time, you are able to understand if this part is going to fail or not fail on a regular workstation. Now, that is solving or answering the distortion part of the problem that I had introduced earlier as possible failures that can happen when you're working with additive manufacturing. And before I jump into the validation of how we have proved that this method of doing multi-scale simulation actually works, let me also show you how this way of solving the problem can also answer the thermal-based problems that you can see when you're working with AM. What you're seeing on the screen right now is basically how, when you're doing this small-scale solve, we are also able to capture and store the peak temperature of what's happening inside your build. What this means is that because we are capturing the thermal side of the problem too, we are capturing the process parameters of your machine and then mapping them onto your material, we are able to understand exactly how hot or how cold your material gets as your machine is printing it. That means that at any given layer, we are able to check, we are able to interrogate and ask if a material got hot enough or did it get too hot. These are the two scenarios that you're seeing on the screen right now. The one on the left-hand side is basically showing you the number of elements that were cold or they did not get hot enough to be melted and hence fuse completely and hence become a solid part that is okay to use. And what you see on the right-hand side of the screen are parts which have basically gone beyond the operating temperatures. They have been burnt and hence they are not usable, or those parts of the part would not be usable. Now, because this is a multi-scale simulation that we do, we are able to apply the learnings of this small scale problem to the large scale too. So we just don't know this information for every layer, but we're also able to check it at the complete part level. And what that means is that we are able to get a full picture of what happens to your part as you're printing it. And these problems become more important to look out for when you're trying to come up with new printing or processing parameters for your machines, or you're trying to come up with new kind of materials to print with. If you look at the scenario on the left-hand side, you'll see that if you try to print aluminum on a steel plate that is not heated, what happens is the bottom layers, let me just zoom in there, the bottom layers are not getting hot enough. That is what this is showing, that this bunch of layers at the bottom did not reach the required temperature. Why wouldn't they reach the required temperature? Because aluminum is a more conductive material. And if you don't heat it enough, or if you don't have it at a certain entropy, any energy that you supply to it will be first used to heat up the material and the build plate and everything else. And only then would that be used to actually start doing the work of melting it and doing the print. And that is what you see happening over here, because you chose to print it on a build plate that was not heated. And on this side, this is basically printing Inconel, where we are applying the parameters that are more applicable for these thin sections, but we're applying it on these fat, large sections. Now, why would that be a problem? That's because when you're printing thinner sections, you generally tend to operate at a very slow speed and at slightly higher power for your laser. That's because you're trying to ensure that all your powder over there melts, becomes 100% solid, so that you get a good part over there. However, as you move to the fatter sections that you see up top over here, you can either speed up your laser or lower down the power, because you now have a lot more cross section that you're burning with the laser, and you don't need to operate at the same parameters as the thin area. But if you choose to do it over there, you're going to end up increasing the temperature too much. You're going to end up burning the powder there. That's what we are showing you. This looks like this over here. These black marks on the real life build indicate that something has been burnt. And that generally means that you have taken that section of the part beyond its recommended operating temperature, and that part is compromised. and that is not something that you want. Just to kind of wrap it up before I jump into the validation, as you saw that using this approach, you're able to solve not just the distortion problem, but also the thermal problem. And you are able to do it in reasonable frames of time. And that's because of our novel hex 8 elements and of the multi-scale modeling approach. Now, since we have used these two new ways of doing things, we had to validate it. We had to prove it out that this actually works the way that we are saying it works. And we did that by doing a whole bunch of experiments. And I'll be sharing links at the end of this so that you can go and read up all about this yourself. But in a brief overview of the kind of experiments that you did are shown on the slide. What we did was we modified an existing M280 EOS machine. That is what you see over here. On this machine, we mounted a box. Inside this box, we put a computer, or basically something that captures data and stores data. And we attached temperature sensors and displacement sensors, which come out of the top of the box like this over here. This is basically what is over here. You see that we have modified the build plate, and we have a new plate which resides on top of the box, which has a hole through which you get some sensors. And on top of that, we have a new thin build plate that we made, which is this really thin piece of aluminum that you see. And on top of that, we are printing a very, very, very small geometry that you see over there. As you can already guess, what we're trying to do is we are trying to make an example or a physical experiment of what we do in the small scale modeling, which is the PRM version of the solve that we showcased earlier. Now, why did we do it like this? Why did we print things on a very, very thin build plate with lots of sensors attached to it? And that's because we were trying to capture what would happen when you are basically printing every layer. And we did it on a small build plate, which is very thin, because as your layer is melting, you are basically expanding everything. Your metal expands, and hence also the build plate that it is building on will expand. And when it is cooling, and this cooling happens when the recoater moves back and forth, things contract and they just shrink, and then you see that it's cooling down and moving downwards, as you see over there. Now, we captured this with the experiment with having these physical sensors in place, and we also did the same thing on the solver. As you can see that both these things are very closely following each other, not just on the trend, but also very closely having the same value. Not in all places, but in some places. So basically, very high correlation between the simulation that we did, which you see as the image up top, and also a cross section that you see over here of the physical experiment, which captured live data of temperature and displacement as the part was being printed, or that little tiny cube was being printed. Now, with this, we showed that, okay, whatever we are doing at the PRM level is working out fine. We are capturing the right information. But are we also passing that same information accurately to the larger scale? Are we also doing the same thing when we actually print a real part? And that's what we did with this experiment. Now, a lot more experiments were conducted. In total, I believe we have done more than $9 million worth of printing and testing and validation for different materials. And a kind of summary or sum of this can be found in the America Makes report, which I am referring to at the bottom of the slide. And some more can be found in the various research papers that the development team keeps putting out, which I'll be sharing the links to at the end of this. But this is just one of those things. So in case you want to see more examples, I highly recommend following this rabbit hole of reading this report or going through these research papers to learn more. But what you see on the screen right now is this fin geometry, which is hollow on the inside. And what happens when you try to print something like this is you end up with a geometry that you actually want to print, which is depicted by these red lines. So this is what you actually want to print. And this is at this cross section over here. But because of the way that the AM process works, you will always end up with a very, very badly distorted geometry, which we printed and then we scanned. And you can see that the scan is represented by the green lines. So you can see that it distorts to a point that what is supposed to be following the red shape actually results in the green shape. And then we also did the same thing on our solver. We also ran a simulation for this, and then we compared the two results. And what the simulation showed was the blue line. You can see that it very closely follows what actually happened in the real world, where you input the red geometry, but what you get as an output are these green and blue geometries. And this, as you can see, was completed on a 4-core machine, very much similar to the laptop that I'm using right now, in 30 minutes for a regular size part that you generally print when you're manufacturing with additive manufacturing. All right, so those are some quick kind of introductions to how we validated this stuff, but I guess that's enough of me talking. Let me jump into the software and also show you how things happen over there. Now, I have a part already loaded up over here. This is just a sample test part. There are multiple ways of dealing with getting geometries into Netfabb Simulation, and I'm not here to discuss those. But we'll simply have a look at how do you actually use this tech, or how do you actually use the solver. In kind of essence, it's very, very straightforward. You simply start off with setting up things over here, and then you process from left to right till you come to the solve button. So you just go through these options one after the other till you're at solve, and then you'll click solve. And it's as simple as that. So let's just go through it. Let's first have a look at the material and the process parameters, which actually is not something that you need to set up unless you're dealing with newer materials or coming up with your own process parameters. But we supply you with a library. So we give you certain materials that you see over here with certain pre-filled properties. And at this point, it's important to note that these properties are not just singular room temperature properties, but they are stored over a range of temperatures. You can see that it is stored over a whole bunch of temperatures that this material will go through as you're printing it. And that is why it's important to understand that we are able to do this whole thermal solve and link the thermal solve with the mechanical solve, because we are capturing this whole bunch of information about every material. If you don't have this information, you don't get the right outputs. You will not be able to capture all that this material has to go through as you're printing it, and hence your solves might not be the most accurate. Just something to keep in mind in case you're trying to add your own material, which is fairly simple to do. You'll just click new material and then input these properties. Once you have your material set up, you can also set up your processing parameters or your PRM file. We supply you with some defaults. These are the most commonly used material plus processing parameter combinations that most AM machines use. However, in case you would like to make your own, you simply click on that icon and then you can go through simply entering up the values. And once you're done, you'll click generate PRM, and then it takes around an hour and a half and you have your own PRM, which will be reflected over here. Now I'm going to assume that we already have the PRM and the material that we're working on. So let's start up by setting up our machine. If you have used Netfabb to pass this information onto Netfabb Simulation, then this option would be selected for you and you already would have your right machine picked. But if you don't, I'm just going to pick this, for example, and it's resize my build plate, and it's placed my part over there, and it will also automatically change the number of lasers based on the machine that you pick. Now, the next thing that you do is you select your process parameters or your PRM file. You can select one thing that is applicable for the entire build, or you can do something that is unique for supports and for parts, or you can have it per geometry where you can have different PRM files applied to different geometry. Since we only have one part on this, which does not really have any supports, I'm simply going to pick the defaults, which is just your Inconel 625, and I'm going to apply it for the entire build. We then set up the build plate. Now here we are defining the physical constraints and the boundary conditions that your build plate experiences as you're doing the build. So that means you first need to fix its size. Now, if you're not printing more than one part, if you're not printing the entire build plate, it is completely okay to simply shrink down to just around your part. So not exactly the same dimension as your part, but slightly larger, just a bit, so that you capture a bit more of the build plate, but you don't need more than that, because that's just empty space where nothing is happening. What you do need to be aware of and capture accurately is the height. And that's because if we go into heating and have a look at the settings that you can have over there, let's have a look at control temperature and set it to 80 degrees, because that's the common kind of setting that's there on most machines. This temperature or this controlled heating is applied at the bottom of your build plate. So that means you have some heating coils over here, and then they start to heat the bottom of your build plate, which then conducts the heat all the way up till the top over here. So dependent on how thick you set up your build plate, the actual heat that your part observes at the top over here is going to vary based on that. So if you're actually printing on really thin build plates, let's say something that's only 15 mm, you should set it up to be 15 mm so you accurately capture that. Or if it's something much thicker, if you're printing on really thick build plates, you should also accurately capture that over there, because that really heavily influences how the temperature profile of your entire part is going to be calculated during the solve. I'm going to leave it at 25. I'm not going to change it. But in case you have unique properties that you use for your printer setup, please capture them. The other thing that's important to note is the fixturing or the constraints of your build plate. And that means, is your bottom of the build plate constantly fixed, which is not the case in most kind of builds, but in case it is, then you need to have that. Or do you have bolts that hold it down in the four corners? This is the most common scenario that people use, and you can always use this as a default if you want to. In some printers, like the concept laser machines, I believe, you just have a central fixture, so that you just have one thing that fixes at the center. And if that's the case, then you can use this setting. But in most machines, you just have bolts on four corners, and you will leave it at that. The final setting that you have to set up is the material of your build plate. And that depends again on the way that you're printing it. If you're printing on the same material that you're actually making the part in, then just leave that check mark on. If not, if you're using a standard build plate, it is mostly in steel of the 304 grade. So just select that. Once you're done, you'll click OK. And now we are done setting up your machine as you do in the real life, setting up your build plate as you do also when you're setting up your AM process in real life. The final thing that we need to set up are the temperature or the thermal boundary conditions. Now, the one thermal boundary condition that happens is during the build process, and that is basically fixed by how you're maintaining the heat within your build chamber. You will either fill it up with a specific gas or just have air in there. And then the convection heat transfer that happens within the chamber based on that is fixed with this value. So you will change this value if you're having a specific gas, let's take argon for example. If you're just keeping it to be air, just leave it at the default. Now, a good thing to note over here is that the solver, for the sake of simplicity and getting the job done faster, assumes that any energy dumped onto the system is simply lost out into the air. So this just goes out. That's it. That's what this uniform heat loss means. The other option that you can have is called conduction to loose powder. What does conduction to loose powder do? Conduction to loose powder assumes that you're not simply losing out heat out into the space which is surrounding the part, but let's assume that you have another geometry that you're printing over here. Now, there will be powder in between these two geometries, and you can have heat conducted through the powder across these two geometries. If you are trying to map this kind of a scenario, then you would use conduction to loose powder, because you will have multiple parts which conduct heat across the powders and across each other and heat up or cool down accordingly, and hence you would use this. However, if you simply have one geometry that you're trying to print, you can use the simple uniform heat loss. This is a decent approximation. There's a third option called estimated heat loss, and this basically is a numerical trick. It's a mathematical trick of sorts, where we have modified the convective heat loss that happens, but we have tried to modify it so that it mimics the conduction heat loss. Now, this basically means your job will get done faster, and it'll be a lot closer to what you would see when you're doing the conduction to loose powder, but it's not going to be accurate. So this is a good approximation, but it's not always the best thing to use. If you're trying to map multiple parts, this is the best option to use. And if you just have one part, simply use this, and it's good enough. So since we just have one part, I'm going to leave it to that. Click OK, move on to the next tab, which is heat treatment. Heat treatment is a common process that you do after most additive manufacturing builds. If you're doing something, set it up. If you're not doing anything, do not set it up. In this case, I'm not going to set it up. But if you were to set it up, you simply have to select this option, and then you need to make your plot of how your heat treatment would work. A typical plot of heat treatment looks something like this. Let me just draw it out there. You would start off by a certain temperature. You would increase the temperature for some time. You would hold it for some time. You might increase it again for some more time. You might hold it for longer, and then you simply cool things down. If you want to make this plot, all that you need to do is capture these points and input them over there. Very simple, very straightforward. Now we are done setting up the physical process. So we have done capturing exactly how you set up your machine in real life. We have simply copied over the same setup into our virtual simulation. What we do next is have a look at what do we want to solve. We would like to solve both thermal and mechanical, because we want to understand not just the thermal problems, but also what happens with the mechanical distortion. We need to define something called as the Recoater clearance, and I'm going to explain that in a while. And then that basically helps us understand if the part is going to hit the Recoater or not. If you want the solver to stop when the Recoater hits, you can simply select this. If not, don't select it. If you were to have support structures in the solve, then you can also set up a failure criteria for the support structures. In this case, we don't have support structures, so we're not doing anything. And then you have a few other extra options that are there for very large parts, where you can calculate anything that might happen due to buckling when you're making a large part, or if you're taking a pause during the print process as you're making the large part, you can set it up. This is a very small part, so we're just going to ignore those properties. The final thing that we have that you might want to take note of is the plasticity. There's something called structural plasticity, which is off by default. If you select it to be on, That means we calculate the plasticity of the entire part as a whole, and we are interested in what's happening to the part even after it is cut off. If this concept is too novel and foreign for you, simply think of it as a way that, are you interested in understanding the residual stresses that this part would go through after print? If yes, you need to select this to be on. If no, keep it to be off. We have this option because keeping it on and calculating it means a little bit more time. And in case you're not interested, then you can keep it off. For the sake of this demo, let's keep it off. Let's click OK. Let's go to the mesh settings. We have a very simple way of calculating the mesh, and that means you need to know what is the thinnest section of your build, and you need to enter that value over here. I know that this build has a thin section of 0.8, so I'm going to simply enter that value, and then it will calculate the mesh accordingly. And the only logic or the only thing that it needs to note as it's calculating this is it needs to ensure that it has two mesh elements, two of these hexate elements that we discussed earlier, that can go through this thin section. So by simply entering this value as 0.8, the solver knows that it needs to make the smallest element to be 0.4, so there can be two elements that go through this cross section. Where this cross section is, the solver knows how to figure it out and add it there. We don't need to worry about it. The only options that we do need to worry about are accuracy. This controls the adaptivity of the layers. So do we want it to be very, very adaptive or not too adaptive? That's what this means. If you set it to be fast, it's going to be fairly adaptive. If you set it to be accurate, the most accurate, it's not going to be so adaptive. There's also something called maximum adaptivity levels, and this is more of a global control of adaptivity. So while this controls adaptivity at a local level, or what happens during every layer that is being solved, this controls what happens at a global level. And that means what happens to the really fat parts of your build, which is the build plate in this example. Let's just keep it to defaults. You don't really have to worry about this unless you're doing very, very small parts or very, very large parts, in which case you can read the user manual and they have some specific settings for you. With that done, I'm going to save this. It's always important to save your work before you click solve, and then simply click solve. And while it's doing the solve, let me get to one of these settings that I mentioned that I'll be coming back to later, which is the Recoater tolerance. What does that mean? The Recoater tolerance, the concept at least, is explained in this slide. Let's start with scenario A. This shows that when you print, you assume that as your last layer is printed at any given point of time, the new layer, or which is where the recoater has to move, which is what's marked as current layer, there is absolutely zero overlap between that and the previously built layer. Now, obviously, that is something that is a very ideal scenario. It's not something that happens all the time. What can happen is that you will have a certain amount of overlap. And the certain overlap is the more realistic, more practical scenario. It happens all the time, where a certain amount of your previously built layer is going to enter into the area where the new layer is supposed to be, or where the recoater is supposed to move. This is where the recoater will move. And that is okay, that there's a certain overlap. This is accounted for in the process. This is accounted for in the machine. And the recoater simply just bumps over it and continues moving. Now, what can happen, and which is where the problem starts, is scenario C or D, where your previously built layer goes over what it's supposed to be occupying so much, or it overlaps so much with the new layer that needs to be built, that there's a 81% overlap, for example. Now, if this were to happen, this is a problem, because that means if I were to draw things out, let's assume this is the recoater. It needs to move in this space. And as this recoater is moving, now there's a large bump over here. This large bump is what this 81% overlap could be. Now, as this recoater comes towards this, this is I mean, this Recoater is not set up to kind of go over this in this manner. It is obviously going to crash. It's going to crash. It's going to break the Recoater, and it's also going to break whatever part that's been printed over here. And this is also what's been explained in this last scenario over here, where something that is so kind of distorted, so much overlapping with the other layer, that it just causes the Recoater to hit. Now, this is what causes the Recoater problem, and that is what you're trying to teach the solver by defining the Recoater tolerance. Are you saying that you're okay having just a slight amount of tolerance, or you're okay having a much larger amount of tolerance? There is no set answer for any machine. This is kind of dependent on your engineering judgment on what you classify as failure. Some people think that going beyond what is a practical scenario, which is 15 to 20% overlap, or a Recoater tolerance of 80 to 85%, is already a failure. If that is you, then you will set it up to be 80%, which is what we did right now when we were doing the solve. However, if you feel that you can give a little bit more leeway, you can have a little bit more give in the system as you're doing the solve, and you think that it can go up to 30% or 20% tolerance, then you will set it up accordingly. But the solver will only show you failure based on what you set up. Just know that. All right. And as the solve is happening, just to give you an example of also what happens when you have the conductivity through the loose powder setup, what kind of differences you can see with those two settings. I'll use this slide. This shows the scenario of printing 3 of these pieces that we had or we have set up, but 3 of them, not just one single one like we're doing right now on the software, and them being run side by side simultaneously like this. Now, when we actually do the solve, and let me just zoom in over here to show you, when we did the solve with the solver, we got the results as shown with the black dots. So the black dots over here showed exactly what the solver said should go wrong, which is this over here. But what we actually captured while printing the part and then scanning was the green lines. So you see that there was there was a significant amount of discrepancy between what the solver was saying should happen and what was actually happening in real life. We tried to change certain parameters in the solver, which is what you see with the red line, but similarly bad results. And this is because we were only capturing what was the convection loss. As I explained, that we assume that heat that is not used for doing any work simply dissipates out of the part into the surrounding air. However, once we started to model in the powder and model in the conduction, we saw that we were getting results which were a lot closer to what was happening in real life, which is what you see over here. So this conduction to loose powder was then a feature that was added, and hence you see it. And this lets you basically model in the powder. As you see, the powder is now modeled in as elements, and we are calculating the conduction through the powder across all these elements, and that gives us basically much more accurate results. But what that also means is that you have a significantly longer solve time, or you need to solve it on much more powerful machines. As I showed you, or what I'm doing right now, I'm solving this part on my standard laptop. However, if I would like to solve it within quick times with the conduction to loose powder, I would need to use a much more powerful machine. All right, so the solve has finished. Let's have a look at the results. We have a whole bunch of different result types explained over here. The most common thing that people are interested to understand is displacement. And while displacement is selected, if you're keen to understand which or what property of displacement we're actually working with, it's there within plot settings. You can select either of the components or simply keep it to magnitude. We can look at a local range, which shows us what's happening at that layer, a more global, or something specified where we can specify a range. Let's say we're looking at only plus minus 0.2. And you can cycle through the start till the end. So you can see exactly how this part behaves as it's building up. And you get this nice little indicator over here that shows what's happening. So it's still printing. And after that, it will cool down and it will stop printing. And then it's called substrate removal, which means it's being removed from the build plate. And you can see that for most or the majority of the part, as it's printing, it's fine. But once we start to remove it from the build plate, or when we actually remove it from the build plate, is when the problems start to occur. And then it's mostly around this band over here. And that's to be expected because that's where we transition from the really thin to the fat cross sections. If it's not evident, we have the options of making a clipping plane. So you can see by cutting into it, or you can also do by removing the element edges so you can see what's happening on the inside. These are just some tricks for you to better visualize what actually happened during the build process. And you just have the option of seeing not just displacement, but also your Cauchy stresses, your Recoater clearance, since that is something that we were just talking about. So we see if it is on a global level, was it mostly okay from the Recoater point of view? It was only certain areas that did a dip to below 80. If you want to have a look at what that meant, it meant like in those areas we had some Recoater problems, which you can see by cycling through specifically the different layers. As you did with the distortion, you can also do that with the Recoater clearance, or with basically any other kind of results that you see over there. Now, these are all very interesting results, and obviously they matter for analysts who are out looking for specific ways to improve the part. But what can you do? What can you do as just an engineer who's trying to understand how to better design or better make your part with additive manufacturing? And that comes with this option over here, which is what most people are after, which is called warped STL. Now, this warped STL basically makes a pre-compensated geometry, and it's done with a simple button click as that. You'll click OK, and it will make you a warped STL, which you can then print. Now, the warped STL is, like I was saying, a pre-compensated geometry. What does this pre-compensation mean? Let's have a look at this scenario where if you want to print this geometry, you would print it and you will see that it'll fail or it'll distort in these areas, which are highlighted as purple over there. Now, if you were to simulate the part, we also show the same failure, but if you make a warped geometry, you will end up with having something which is essentially moved in or pre-compensated or pre-warped in the opposite direction. So we basically squeeze it the other way so that when you print it, you actually get it to more or less in line with what you wanted to see. So you now see that over here, this thing is going to be straighter as compared to what you did if you actually printed the actual part that you wanted to print. This is just a very overly simplified part and a very overly simplified example, but I hope it illustrated the point. This works really well for really complicated geometries too. So if we have a look at this, which was the very complicated fin that we saw at the beginning, which distorts very badly, if you print it with the compensation model, you get it in line with plus minus 0.1 mm, which are acceptable tolerances for most additive manufacturing machines. You also see it with the case over here where you had distortions up to 0.6, and then with the compensation we managed to get it up to plus minus 0.2. Also removing these kind of lines. And these are basically the kind of things that people are after. People are after a way that you can run a simulation, get an understanding of where things will go wrong, and simply make this compensation geometry. And this is what you get to do with Netfabb Simulation. it all culminates down to that one button, and that one button gives you improvements like you see over here, where if you don't print it with the compensation, you get lots of failures, but if you print it with the compensation, you get much less failures. And with that, I will end this session with just a call out for a bunch of more resources and extra content that you can access and read up about. These just basically go into more tutorials and more details, like I had promised, that that either provide more information about how we did validation or provide you with more information to follow up on and better use Netfabb simulation. Thank you.